So with that, I'd like to introduce Thomas Frolicher, who is coming to us from ETH Zurich and soon to be University of Bern in Switzerland. So thank you for coming.
Thank you.
Your mic on?
Yes. Does it work?
It says to be on.
Yeah, it should be on. Yes. Okay, good morning, everyone. And thanks, Andrew, actually, for inviting me. It's the first time being here. It's a real pleasure for me. So I also want to thank first my collaborators on these projects. So first, Keith Rogers from Princeton University, and then also Charlie Stock from GFDL, and William Chung from the UBC in Vancouver, and Nikki Gruber and Eric Fischer at ETH. So I'm going to talk about large-scale natural variability and anthropogenic trends in multiple ocean ecosystem stressors. And I want to just start broadly. So we all know that the ocean takes up about 30% of the anthropogenic carbon we emit into the atmosphere due to fossil fuel burning and land use change. But the ocean also takes up about 93% of the excess energy since about 1970. And due to the increase in greenhouse gases. So as such, the ocean actually gives us a huge service in keeping the climate cool, but this huge service comes at the cost of profound alteration in its physical, biogeochemical, and ecological state. So the uptake of anthropogenic carbon leads to ocean acidification, as you all know, decrease in pH and decrease in calcium carbonate saturation states. The uptake of excess energy leads to warming, mainly of the upper ocean, and together with a freshening of the polar ocean, this leads to a reduced ventilation of oxygen-rich surface water to the deep ocean, and together with a reduced solubility of oxygen in warmer waters, this also leads to deoxygenation. And also, because of this increased stratification, there is a reduced resupply of nutrient-rich deep water to the surface, and we also expect net productivity change. So here you see a compilation of 10 different CMIP5 models, which they project these multiple stressor changes into the future for different scenarios for the RCP 8.5 and 2.6. And you see that all models actually show a continuing acidification, a continuing warming, a continuing deoxygenation, at least averaged in the thermocline, and also somehow a decrease in net primary productivity. So we can actually summarize the ocean is warming up, turning sour, and losing breath. And Nikki always calls that the quadruple whammy for ocean life, because it can have severe and sometimes even irreversible impacts on marine organisms and ecosystem services. So for example, it can also have impacts on higher trophic organisms such as fish, which I will show you an example later, where we show that actually the fish catch potential will decrease about by 3% per degree warming globally. And that's why the IPCC has just recently summarized that the marine organisms and ecosystem services will actually face high to very high risks under increasing global warming levels. Okay? So here you see this burning ember diagram. So during my talk now, I will talk about the sources of uncertainties in these projections of multiple stressors, or how important are actually natural variability on a global and regional scale. Then I will make a short excursion and talk about what are the impacts on marine fisheries, or what are the benefits to marine fisheries of meeting, for example, a 1.5 degree global warming target. And then I want to talk about, which I think is so far a little bit an overlooked potential serious problem. I will talk about the ocean extreme events in these ocean ecosystem stressors. Okay, let's come back to this figure I've shown you before. So here you see all these projections again, and you see that these climate model projections have large uncertainty. And so you see here, for example, net primary production, some models show a large decrease, some models show almost no decrease, or even an increase. And the same also for oxygen, there's quite a large uncertainties. And these changes also occur on top of regional and natural variability. So what we did, or what decision makers first And regional impact assessment modelers usually want to know is how, the quantitative projections of future changes in these ecosystem stressors, especially on regional scale and over the next 20 to 30 years. So we were asking in this paper, which we just recently published in GBC, what are the sources of uncertainties in these projections? And does actually the source of uncertainty vary with region, with time horizon, and the ocean ecosystem driver variable? So what are the sources of uncertainties in these projections? So first we have the natural internal variability. So for example, different ENSO cycles, changes in the NAO, AMO, or SAM, or changes in storminess on smaller time scales or spatial scales. Then we have the scenario uncertainty, so different future scenarios will give us different changes in these multiple ocean ecosystem stressors. And then we have different models, as we have seen yesterday already. So they have quite different complexities. So here are different the ecosystem models which have been used in the recent CMIP5 exercise, and you see that they have totally different complexities. So some have more than one zooplankton type, others have just one different phytoplankton type, and so on. They also have different complexities in the physical climate. So now we want to understand what are the different sources of uncertainties in these projections. Is it internal variability, is it scenario uncertainty, or model structural uncertainty? And to get at internal variability, so the natural component of the variability, we run a large ensemble with the GFDL model. So what we did is we run the model from 1860 to about 1950, and then we perturbed the initial condition by really a tiny amount, by 10 to the -5 in SST, for example, in the Weddell Sea. And then we run the simulation 40 times with the same boundary conditions, but with slightly different initial conditions. And then the spread among the ensemble gives you an indication of the internal variability. To illustrate you that, I show you here the projected SST changes in the Humboldt current system. So that's a really productive system of this large ensemble. And you see here the thin line shows you the single ensemble member. That's the multi-ensemble mean, the solid line here. And if we just focus on the next 40 years, for the period 2000 to 2040, and we look at the outliers, you see that one single ensemble member actually shows almost no change in SST, whereas the other one shows a change of about 1.2 degrees. That's just because of natural variability. So this is kind of an irreducible uncertainty which we cannot really reduce, except if we are somehow successful in predicting, with initializing with the model with data in predicting the next 20 years or so. So what we then did is we compared these different uncertainties with each other for pH here, for temperature at the sea surface, for oxygen averaged in the thermocline, and net primary productivity. And the x-axis shows you the time. And you see that at the beginning, internal variability is quite important, and also model uncertainty. But then for pH, scenario uncertainty becomes quite rapidly dominant, because the surface pH is mainly bounded to the atmospheric PCO2 changes, and in the RCPs, they diverge quite rapidly. Then for sea surface temperature, actually internal variability on a global scale is quite important already in the next few decades, and also model uncertainty. And also the same picture appears for oxygen. For net primary production on a global scale, it actually doesn't really matter which scenario we follow. It's mainly the model which actually really show different responses, and also the internal variability, which is really important. Now if we go to the local scale, just averaged over the large marine ecosystems, you see mainly that actually the orange area here becomes more and more dominant, especially for sea surface temperature and oxygen, and also on net primary productivity. So on local scale, this natural variability is even more important. Now you can ask the question, okay, so when does then the signal moves outside of the internal variability range? And we looked at the time of emergence of these stressors out of the natural variability, and we defined the time of the emergence as the signal-to-noise ratio when it's bigger than 1. And the signal is just the changes, the multimodal mean changes for the RCP 8.5, and the noise is the internal variability plus the model uncertainty. And here you see the time on the x-axis. On the y-axis, you see the proportion of the ocean area with a signal-to-noise ratio bigger than 1. And you see that actually pH already emerged out of the noise because it's such a strong signal. SST has already emerged as well, and actually 92% of the ocean areas will emerge out of the noise by the end of the century. For oxygen, it's only about 23% by the end of the century. And for NPP, almost no single grid cell actually has emerged out of the noise. And combining these four stressors, about 54% of the whole ocean area actually emerges out of the noise. When we look at the spatial scale, just focusing on SST and oxygen, we see that mainly the low latitudes will actually face novel conditions quite rapidly, especially over the next 20 to 30 years, whereas in the high latitudes, the uncertainty is too big. A little bit a different picture emerges for oxygen. So here only the high latitudes, some parts in the high latitudes actually emerge from the noise by the end of the century. So now I want to talk about a little bit about the impact on these changes in these ocean ecosystem stressors on marine organisms and especially on fish. So what, as you all know, about 197 parties have ratified, well, have actually agreed in the COP21 to hold the increase in global mean temperature to well below 2 degrees above pre-industrial levels, and to pursue efforts to limit temperature even at the level of 1.5 degrees. And so far, 147 parties have ratified this convention. And as you all know, that probably the second biggest emitter will probably not be part of this agreement. Now you can be very disappointed about that, or you can also ask the question, well, actually, were we as a community not convincing enough yet to really show the benefits to stay below 2 degrees? That's actually what we wanted to do. We wanted to translate the Paris Agreement into impact-related targets to facilitate the communication of the benefits, okay? Based on the example of the fish catch. And this has just been recently published in Science. So we were asking, what are the benefits to fisheries of moving towards the Paris Agreement target? So what we did, so we took these Earth system model projections of these multiple ocean ecosystem stressors for the two different scenarios, and we actually run an ecological niche model, so the marine species distribution model, the DBEM, that simulates actually the interactions between the changes in these multiple ocean ecosystem stressors, ecophysiology, population dynamics, dispersal, and habitat productivity. And we applied that to more than 900 exploited fish in invertebrates. Then we looked how the maximum catch potential will change under future global warming. And if we plot that against atmospheric temperature, so maximum catch potential is actually a proxy for maximum sustainable yield in this model. So what we found is actually quite a nice relationship that the change in maximum catch potential is negatively linearly related to atmospheric temperature, and the catch will decrease by about 3% per degree warming. So that means about minus 10 to the 6 tons per degree warming. Now you can say, well, that's not so much, 3%, but actually, first, so if we look at the 3.5 degree, which we will have with the current emissions, that would give us about a decrease of about 8%. So if we actually move to a 1.5 degree target, So there's a large benefit to the catch potential. So we will actually reduce the change only to about 3%. But as I said before, so there are large regional differences. So mainly in the low latitudes, there's a large decrease in catch potential and also a large benefit for actually holding the temperature below 1.5 degrees. That's mainly, it has to do because the fish will move towards colder waters or they get extinct. In the high latitudes, there's a change in maximum catch potential is projected to be positive because there's a gain of the fish which will move to colder waters. So actually these countries will probably, countries which lie in the high latitudes will actually have not a benefit of actually reaching the 1.5 degree target. But there are also some non-linearities in the system. So for example, in the Norwegian Sea, because of sea ice retreat in the future, that will actually increase the growing season, increase net primary productivity, and increase the catch at the beginning. But then the water warms, especially the surface water, which increases stratification again, and actually reduces the resupply of nutrients from the deeper ocean. And that's why at a certain warming level, actually the catch really drastically decreases. And I think the nicest thing about this study is that actually, at least in our model, this is a linear relationship, so between the change in global catch and atmospheric temperature. And as we know, atmospheric temperature is also linearly related to cumulative carbon emissions. We can actually replace the x-axis here with cumulative carbon emissions, and we can actually say or state the impact of 1 ton of CO2 emissions on fishing catch. So we can actually attribute each change in catch potential globally to a country's emission. Yes. And now I want to talk also a little bit about, I think, a so far overlooked problem in our community about ocean extreme events. And as you may know, the IPCC has concluded that extreme weather events such as flooding events or heat waves, the risk of these events will actually increase with increasing global warming levels. And this has been just in 2012, there was a special report on extreme weather events. And this report actually was 522 pages long. And I was looking through this report, and only one page was about ocean extreme events. And actually, this was dealing with wave heights and sea level rise. Well, actually, there was no mentioning about ocean extreme events in these multiple ocean ecosystem stressors. So we don't really know how ocean extreme events will change on the future global warming, and what is actually the impact on these ocean extreme events on marine organisms and ecosystem services. And the Swiss National Science Foundation has just recently funded a project, it's called OceanX, where we will actually investigate that. And our hypothesis is that if we combine that together, that marine organisms and marine ecosystem services will face much higher risks on the future global warming levels than previously thought. So far, our understanding of ocean extreme events on marine organisms is mainly based on marine heat waves and their impact on organisms. So here I made a quick compilation of just recent marine heat waves which has been occurred in the global ocean or observed. So you may know all this, the warm blob in the North Pacific, which has occurred in 2014 to 15. But there was also a heat wave hitting the east coast of the US in 2012. There was a Mediterranean marine heat wave in 2003 due to the strong strong warming in summer in 2003 over Europe. There was a really strong warming off the coast of Peru just recently. There was also strong warming in 2011 off the coast of Australia. And there actually the sea surface temperature was about 2 to 3 degrees higher than usual for a duration of about 10 weeks. And before the heat wave actually hit the coast, the ecosystem looked like this. It was mainly dominated by kelp forests. But then when the heat wave actually hit the coast, seaweed turf took over and totally replaced this ecosystem which was there before. And it hasn't actually recovered yet. So it still looks like this off the coast of Australia. So heat waves can have a really significant impact on the whole marine ecosystem structure. So what we did so far in this OceanX project, we were wondering, does actually anthropogenic warming changes the odds of the marine heat waves? And usually we define extreme events in the tail of the distribution. So here you have a frequency distribution of sea surface temperature, for example, in the pre-industrial, so in the natural world. And we define the extremes here in the tail of the distribution. Okay? So above a given threshold. It can be a relative threshold, above a certain percentile, or above a fixed threshold. For example, for oxygen, we have a really good understanding what the fixed threshold could be. And what we then did, so we have a probability that an event or a probability that sea surface temperature is above this certain threshold in a natural world, so in the pre-industrial. And we have a probability that the event will occur or will be above this threshold today and in the future. And what we then did is to calculate the probability ratio, so P1 divided by P0. And we also calculated the fraction of attributable risks. So that's 1 minus P0 over P1. So that means if it's actually 1, that means that all extreme events which occur today, for example, in comparison to P0 in pre-industrial, can be are attributable to global warming and therefore to human-caused greenhouse gas emissions. So when we look then at when we define a heat wave with the 99th percentile, so I have to mention probably that I used daily SST data from more than 10 CMIP5 models over the period 1860 to 2100. And when we look at how the frequencies of the events per year will change over the course of the historical period into the future, here we have two definitions of a heat wave, so a moderate heat wave and more a really hot extreme. So a moderate heat wave, that means it's an event 1 in 100 days, and with this definition it's an event 1 in 27 years. And when we look how the frequency will change, we see that what used to be a 1 in 100 day event here will become a 1 in 2 day event under the RCP 8.5 scenario, so a large increase. And if we really go to the hot extremes, so that's globally averaged, what used to be a 1 in 27 year at pre-industrial, we become a 1 in 3 day event under RCP 8.5. So if we then plot the probability ratio here on the y-axis against the global mean warming for the different, for the moderate extremes and for the hot extremes, you see there is a large increase in the probability ratio, especially for the very hot extremes, but not so, well, also a large increase for the moderate extremes. And we're already today at the 1 degree global warming, about 90% of the moderate marine heat waves are already attributable to warming. So when we look at the spatial pattern for today, so in 2005, and for the future in 2090, and for the low emission scenario, which gives us about a warming of 2 degrees, and RCP 8.5 scenario, which gives us about a warming of 4.5 degrees globally average, we see that mainly the probability ratio really increases in the low latitudes, not so in the high latitudes, because there the warming is not so pronounced. But also in the Arctic Ocean, in the future, we will have a strong increase in extreme events because of the strong warming, but also because of the increase in the variability. So it's not just the mean shift which can change the probability of an extreme event, it can also just by changing the higher moments of the probability distribution. So it's actually more likely that we have moderate extreme events in the low latitudes already today than in a natural world. And we'll be much more likely to have it in a future world in 2090 under both scenarios. We also looked at satellite data from SST. Can we actually see that already in the data? We looked at the SST satellite data from 1982 to 2015, and here my master student David Kessler did that. So he defined the heat wave a little bit differently. So he looked at the 90th percentile, and the heat wave has to last at least 4 days in a row. And so that was based on a definition just recently proposed by Humboldt. And what we see is, globally averaged, with this definition, we have about 1 event per year in 1982. And this has significantly increased to today of about 3 events per year. So there is already a doubling based on this definition in marine heat waves globally over the satellite period. So to conclude, future projections of potential ocean ecosystem stressors are fraught to large uncertainty, and the internal variability is actually the dominant source of uncertainty, especially in middle to low latitudes and in most coastal large marine ecosystems in the next few decades. So that means there is an irreducible uncertainty inherent in these projections. Then operating within the Paris Agreement substantially reduces the risks of impacts on fisheries. And global warming has already significantly increased the odds of marine heat waves to occur. Thank you very much for your attention.
Time for questions.
So kind of great talk, and then so kind of thinking of like observations that I could maybe see like the observation trend. How do we know from an observational point of view if it has gone out of the uncertainty range or the natural variability range as opposed to an actual detectable trend? Is there like any insight you can give us from the modeling side?
Well, from the modeling side, we know from the pre-industrial conditions that that's the natural world.
But let's say we see a like decreasing trend in oxygen. How do we know that that's, you know, part of a natural variability event within the climate systems versus an actual attributable trend to anthropogenic activity? Can we ever do that when we have an N of 1 in the real world experiment?
Yeah, that's a tough problem. So what we usually do is when you assume that the model gets somehow the process is right, you can actually run these large ensemble simulations, and then you get like different projections or different, over the last 30 years, you get simulations with different natural variability, and so different trends. And actually, if your observed trend is actually greater than the natural variability you get from the spread of the ensemble, you can somehow say that that's a detectable trend due to anthropogenic climate change. But then you have to assume that the model gets the mechanism right.
So you were saying that there's about 5% difference between the RCP, like business as usual, and the 1.5 degree warming for fisheries. But you also said that the time of emergence for MPP was more than the year 2100. So, like, given the huge amount of internal variability in your system, how do you reconcile those differences? Like, how can you make a reasonable projection on the impact of climate change on fisheries?
So the DBM model we use, that's actually mainly developed by William Chung at UBC. So what we see mainly, so the fish changes mainly respond to temperature and not really to NPP in our model. And that's why the temperature actually merges out from the noise much faster than NPP. So that's the main reason.
I think in the interest of time, if it's a quick question, maybe we can do it.
Quick, yeah.
Quick.
Okay, I think one of the problems with your heat analysis into the future is that you fail to realize that you've made the assumption of linearity based on your temperate and your Arctic experience, but the tropical experience of fish and their habitat is right near the brink of disaster. This has been known for 45 years at 1.5 above what was ambient in the 1970s. And much of the fisheries is based on a nearshore benthic, and that is based on the habitat. The coral is already dying around the tropical world. So I think you have to go back and look at the tropical portion of your projections.
Well, I would again like to thank Thomas for a really enlightening talk.